Welcome everyone to this afternoon session of the summer school. And Charles will tell us continuation of the story about the simulation of the continuous fluid dynamics. The floor is yours, Charles.
Thank you very much, Ilya. As you know, we've taken an approach for the previous two lectures of breaking the lecture up into three shorter, called them micro lectures, with the opportunity to have a bit of a conversation in between. We'll carry on with doing that as before. If you've got any questions at any stage, type them in the chat box. And Andrew, I'll keep an eye on the chat box if I can, but Andrew can also interrupt me and we can address the question right there, or he may be able to answer you by text straight away, depending on what you're asking. Right, so we started off with a slightly atypical approach in the sense that I had talked about turbulence modeling before we got much into CFD itself, simply because it's been my experience that that's logically where it belongs, even if it doesn't really belong in that position in a consistent academic approach to teaching the subject. Now I'm going to carry on with that theme in the sense for this next lecture, I'm going to actually start talking about meshing first. One argument is that you can't really do any finite difference, finite volume, finite element work if you don't have a computational mesh to do it on. The alternative way of looking at it is that the mesh doesn't mean anything if you don't have the method already sorted out. So in many ways, it's a chicken and egg situation. So in this case, we'll assume that there was an egg first, and then we'll worry about the chicken a little bit later down the line. So I'm still going to start talking about meshing first. One of the reasons for this is it's been my experience that it's one of the most important parts of working as a CFD practitioner that you really have to master, and it is by far the most time-consuming part of the job. Especially when you're dealing with CAD-related geometries, which you need to turn into CFD models, building a mesh for it is a very demanding task and it takes a long time. So we'll start off there and just a bit of an overview over what we're trying to do with mesh generation. Right, so there are really two parts to discretizing or following the discretization process for computational fluid dynamics. There's the grid, where you've got to take your flow domain and turn it into a discrete representation of a continuous domain. So that means, in other words, we turn it into a grid of discrete points or volumes or elements, however you choose to express it. And then, of course, you've got to discretize your partial differential equations. You need some kind of scheme to turn the calculus formulation of a piece of physics into a piece of algebra that you can solve on a computer. So that's the other way of approaching discretization. So we'll look at grids first. Now, classically, you would take a rectangular domain and you divide it up equally in all directions. The simplest way of starting in this field is to do a one-dimensional steady heat conduction problem. You've got a long rod, one end at one temperature, one end at another temperature. What's the final temperature distribution going to look like? Well, I can tell you it's going to be a straight line between the two temperatures. But you can prove it to yourself mathematically, and then you can turn it into an exercise where you work out how it changes in time. And you can extend the same approach into 2 dimensions and then into three dimensions. But you're following the same approach. You're basically discretizing uniformly in time and space, delta x, delta y, delta z, delta t. And then you use a finite difference method to turn your partial differential equations into algebraic equations, and then you solve it with some kind of method. This is not how real-world problems really work, because you can't represent real geometries in real situations like this, and certainly not very efficiently. There's a lot of advantages to doing it this way. And one of them is that the mathematics and numerics become very easy and they become very fast, especially if you're applying the finite difference method. And using the finite difference method to start with, you can get to the point where you understand a lot more about the numerics of finite methods. So differencing schemes, schemes in time, schemes for solving the equations, all of those are relevant, and they will remain relevant when you move into more complex approaches to computational methods. But you remove a lot of the non-essential complexities by starting with a uniform grid and the finite difference method. Of course, real life very much does not look like a chessboard. It looks more like this, and this is a very simple one. This would be some kind of flow domain. This could be a river, a channel, or some other two-dimensional flow domain. And
sorry,
what?
Charles, I don't know if you meant to show us the screen.
Oh my goodness! Oh my goodness! Yes, of course. Thanks for pointing that out.
Thank you.
Just beat me to it.
Okay, we can just back up a couple of slides. There we go. Sorry about that, and thanks for pointing that out. Righto, so that is the Cartesian mesh, or the uniformly spaced finite difference mesh that we were talking about with its delta x and delta y intervals. And the important thing here is that each node in this grid can be indexed, and it can be indexed relative to its neighbors. So implicitly, you know where the neighbors are and how far they are away. And this is the difference between this kind of grid and the more complex non-structured meshes that we'll get into a little bit later. There you don't have the implicit knowledge of what the neighbors are and where they live. There you need to store it for each grid cell or grid point. You need to store neighbor information. So there's a lot more information that has to be stored with an unstructured mesh than with a structured mesh. So it also means that finding out where your two nodes upstream would be, for example, for applying second order differencing, and we'll look at that in a moment, is already implicitly there. It's just I-2 kind of thing. So it really makes life very simple for developing numerical methods. The catch is it's not particularly physically realistic, because the real world looks a lot more like that. So I was talking about this maybe being two coastlines with a piece of water in between, or some kind of two-dimensional flow channel. It's not really that's not really relevant at the moment. The point is, this is a single block orthogonal boundary fitted grid. So you take those words individually. It's a single block grid, just like the previous one was. So it's got a certain number of I dimensions and J dimensions. It's orthogonal. It's not rectilinear, but the grid lines cross each other at 90 degrees. And that's very important, because it means that our numerics stay valid, because fluxes and things are 90 degree to cell interfaces, for example. You transfer to Cartesian coordinates. You take this whole complicated thing, which is now fitted to your boundaries, and you turn it back into a rectangular domain by means of a Jacobian transformation matrix. So your system for solving the equations remains exactly the same still, but then you modify it with the actual numbers get modified by the Jacobian of the transformation. So this is quite a useful development, because it means all the sort of simple finite difference methods remain valid, but you can do something that's a lot more realistic. And it's quite astonishing to see how complicated a domain you can actually mesh in 3 dimensions with a single block mesh like this. But there are limitations, and the mesh quality starts suffering at some point. The problem, of course, with using finite difference is that you're actually working with grid points. You're not working with control volumes. So you're not necessarily guaranteed to maintain conservation of your properties. When it comes to getting good quality results in CFD, one of the things that you learn quite early on is it's useful if you can keep your flow aligned with your grid lines. It means you've got minimal flow crossing grid lines, which makes your fluxes for your differencing schemes more accurate. However, it's never practical, and if you knew what the flow field looked like before you started building the grid, you wouldn't have needed to do it in the first place. But there are methods that use simplified approaches to fluid flow simulation to give you a grid that's going to be approximately flow following. More realistic is to take your single block grid and to extend that logic into a multi-block structured grid. So we'll stop and talk about this for a moment. You're not going to be using the finite difference method here anymore, probably. You could if you really wanted to, but it's not really where you get the strength of the method from. The strength of the method is you can deal now with arbitrarily complex configurations and geometry. basically the limit of the complexity that you can go to is the amount of skill and patience involved by the person who is setting up that grid. If you've got months, you can mesh more or less anything this way. Normally you don't have months, so we do have better techniques these days. But there are some pretty good reasons for meshing things in this way. You've got tremendous control over exactly what each grid cell looks like. You've got a lot of control over the quality. And there are certain things which just do best if you give them a hexahedral cell for the mesh. So the hexahedral cell obviously has got 8 corners and 6 faces. It's a brick, or it might be a distorted brick in a boundary fitted grid like this. But you very often can use this method, get very high quality grids and very high quality results with a fairly small number of grid cells. It is labor intensive to build though. So I'll give you an example of one here. That looks horrible, and in many ways it is horrible. That is what a multi-block structured grid ends up looking like if you have to deal with sufficiently complex geometry, and there are certain topological reasons why you would want to control exactly where you put the grid cells. So in this case, you've got yourself a sailing yacht. It's a sailing yacht with 2 rudders and a fin, and each of those is obviously of a wing section, an airfoil kind of section. And we know of ways that give you good quality grids around airfoils, and they involve a lot of grid cells to get a nice wrap of the grid around the geometry. Also, because it's floating on water, you'd like to be able to have your grid near the water surface more or less parallel to the water surface and refined in that region. Small directions in the vertical, so small dimensions in the vertical direction. So you've got quite a lot of complexity that you want to handle. What you're seeing in this image is not the grid. What you're seeing is just the edges and the corners, the vertices of the blocks. And it illustrates what happens with a multi-block structured grid. It's logically connected. Everything is logically and topologically connected. So each block is connected to other blocks, and they wrap around bodies. So if you change the number of grid divisions along that particular grid line there, it propagates everywhere else, from there to the vertical fin, to the distance out from the hull out to that one. So when you start working on a grid like this, it gets complex very quickly, and you can get to 1,000 blocks quite quickly. It's impossible to do unless you've got very good software to do it with. But still, it takes time to do. But when you do that, you can end up with a grid like this. It's very efficient because it's putting the grid where it really needs to be, and it's giving you the spacing of the grid refined in the region where things are going to happen quickly. So if you toggle between these 2 images, it's the same boat, more or less under the same conditions, but now with the surface mesh shown. You can't show the volume mesh in the same picture because it would just disappear in a tangle of lines. So a mesh like this would be typically around 5 million cells, but they're very, very highly focused in regions of interest. If you had to do the same thing with a less manual method, using a more automatic unstructured mesh, you would probably end up with an excess of 20 million cells. Because with this method, you can put them where they really need to be. Of course, there's a downside to this as well, because all the lines are connected in terms of spacing. All these bits of grid propagate with that fine resolution out into far away from the body with the same number of grid points where they're not needed. So a long time ago, in finite elements especially, unstructured meshing became the norm. It's become now the norm in fluid dynamics as well. It just needed quite a bit longer to develop the precision numerical techniques that would allow that to happen. So classically, an unstructured mesh is tetrahedral. In other words, it consists of volumes, grid cells, that each have got 4 faces, and each face has got 3 edges. Remember what we said last time? A triangle is a nice thing to work with because 3 points always lie on a plane, and it's easy to hook them up in such a way that they share edges, so it's always waterproof. Well, the same thing applies to the meshing. If you take 4 triangles, they form a tetrahedron. And it's a relatively simple and easy method of filling a complete flow domain with a detailed mesh. Tetrahedral meshing has been used with the finite volume and the finite element methods. Initially, the finite volume discretization processes produced rather poor results. These days, there are much better schemes available. You can do it almost entirely automatically, and it's, of course, the best thing for complex geometry. The downside is that your cell count is very high. You have far more cells, but it's not necessarily the end of the world, because the number of points is not so bad, because the number of points in the tetrahedron is number of points in a tetrahedron is much lower than in a hexahedron, for example. So you may have the same number of points, but far more cells in the tetrahedral mesh. Okay, so I see there's a bit of conversation on the chat box going. Let's just read this question.
Sorry, I think I was unmuted when the dog was.
Does aligning the grid line with the direction of flow only depend on how the grid's created, or also on the geometric orientation? Yeah, they're definitely very closely linked. Well, we've often talked about designing things, aircraft, boats, whatever, that would be easy to mesh in CFD. In other words, before you decide on the shape of the thing, you decide what kind of method that you're going to use to analyze it, and then it'll be very simple to mesh it. Unfortunately, that's really not how real world works. You know, an object is designed for a certain purpose, and then you do the analysis to work out how well that works. You don't design it from the point of view of making it easy to analyze, although there's a certain attraction to doing that. For designing the mesh, you want to look at the geometry. Look, the flow is generally going to follow the geometry. So if the mesh lines close to the body follow the contours of the body, then they are more or less going to follow the contours of the flow, the streamlines of the flow. But there'll be a bit more of that in the next slide. But yeah, tetrahedral meshes have for a long time been the workhorse. But you can extend the tetrahedral meshes by combining tetrahedral cells to form polyhedral cells. And this has become rather popular now. So your underlying mesh generation algorithm is still based on generating a tetrahedral mesh, but then you combine the tetrahedra to form these polyhedrals. And they've got certain numerical advantages because you don't have the acute internal angles. You have a far lower cell count, although you still have the same number of points. So your mathematics and your solver is not necessarily that much faster, but you can get better, more precise solutions this way. Certainly the grids look a lot nicer. They look much smoother. They certainly just look very nice. From a mathematical point of view, it kind of makes sense for the finite volume method. You just got grid cells with far more faces. But it's nearly always built, the methods work on the basis of converting a tetrahedral mesh to give you the polyhedral mesh. So this is now where that method of, or that idea of the grids, of the cell grids, the grid lines following the contour of the body, also meaning that they more or less follow the streamlines of the flow. This is where that rather breaks down. This is a very effective way of dealing with very nasty geometry, which is cut cell meshing. So cut cell meshing evolved principally to deal with horrible geometry, such as what you get in the engine bay of a car. So the OpenFOAM method, for example, the OpenFOAM family of software, includes a mesh generator called Snappy Hex Mesh. Now, Snappy Hex Mesh was the development of Snappy Hex Mesh was funded by Audi, who wanted something for underbonnet flows. And in some ways, it's a very nice method to work with, because you can start off with a block of mesh, and then you just start inserting things. And the method cuts out the bodies intruding into the flow domain, and then it snaps the grid surface or the grid cells onto that surface. There's a lot to that method numerically, and it's quite difficult to get it to do it well. But this has become one of the most popular methods of dealing with real life geometry. But this immediately breaks down that idea, unfortunately, of the flow following the contours the grid lines following both the contours and the streamlines. So we'll talk about it in a little bit more detail later, but in order to resolve what happens near the body surface, we tend to use prism layers. So you take your surface mesh and you extrude it out into the rest of the mesh to give you a prismatic layer of cells, which resolve the boundary layer, and in the near wall region give you grid lines that are more or less parallel to the flow. So it's a way of partly getting around that particular problem. But there are lots of catches to this. And I was sensitized to this by a remark that a friend of mine made. He'd worked together with me at one stage, but then he ended up later on working for one of the Formula One teams. And they were using this method to do their CFD meshes for analyzing aerodynamics of the car. And he made the interesting remark that you had to check the grid quality very carefully, because if this process produced a single bad grid cell somewhere near the surface, it could easily throw out the overall results, which would be typically values of lift or drag, or downforce and drag. It could easily throw out those values by as much as 5%. And that means it's not so much the fact that you've got bad quality grid, but you could have bad quality grid in a very critical area. So you've got to watch your quality metrics here, although it's a very efficient way of meshing because you don't have a propagation of grid lines into the domain. But you do have to watch for this inherently 2-to-1 refinement. So 2 cells convert into 1 cell. And that means that anything that changes on that length scale is completely lost when you get to that size of grid. So I see there's been some questions here.
There was actually a question related to that. I've partially answered it, but I think you should say.
Let's just take a look at the text box here.
The original question was,
does increase the mesh steps would increase the accuracy up to a point? That's exactly what you're trying to do here. You remember I talked earlier about quality control. One of the quality control measures that you need to apply is to check what influence your grid has on the results. So there are lots of other things that can affect the quality of your results, but the grid's very important. And a standard method is to keep refining your grid, make your grid smaller and smaller, which means your solutions take longer and longer, and map out the change in the results that you get with this increasing refinement. So under certain conditions, it'll be a clear asymptotic relationship and it'll flatten off, and you know that's fine enough. There's no point in going finer than that. Under others, you'll find that there's a kind of a logarithmic relationship, that it's logarithmically going to an asymptotic value. In other words, so that you could extrapolate. It's called Richardson extrapolation. So you can estimate what the final answer would have been if you had an infinitely fine grid. So in real life, of course, you never have an infinitely fine grid, but the approach is a very important one, is that you have to actually check whether your grid is fine enough or not. We don't always do that. Very often you know what you're doing the analysis for, and it may not be critical to have grid independent results, but if you're going to be comparing different ideas, they need to be working at a similar level of mesh resolution if your relative answers are going to be reliable. So you should not compare fine grid results to coarse grid results. Ideally, you should always use a grid that's fine enough. Practically speaking, that's not always possible. So then at least you need to be very consistent. And Andrew's comment here, usually want the mesh to be finer where there are large gradients, is extremely important. If you're after good results, it's almost more important to make sure that you've got the grid refined in the regions where things really happen than to worry too much about the overall refinement or cell count. By focusing on the regions that are important, you can get the answers resolved to a high degree of accuracy without needing to resolve to fine up the grid in the rest of the region. So that's a really important point, is that you can selectively do it. Okay. So the other thing, of course, with this cut cell Cartesian meshing is that it inherently gives you a 2-to-1 step in the way that the grid's progressing. So you've got a topology change from here to here, and the solver must be aware of it. So there are a couple of different ways of doing it. So one way would be for this cell to take an average, for example, of these two cells. And the other one would be to say that this cell, this face, this is not a 4-edged face, but actually a 5-edged face, which is how it's normally handled. You're basically breaking up those hanging nodes into two separate edges or faces. Right, so in the real world, things move. All sorts of things move. Aircraft wings deflect, boats move on waves, car wheels turn, all sorts of things move. And your computational methods need to make allowance for that. And there are different ways of doing that. If you've got a very simple type of moving geometry, you could just move the entire mesh. In other words, you've got a single solid body movement. But if you've got relative motion, you've got to do something else in order to accommodate that motion. So when you do the solid body motion, in effect, you allow the boundaries of your entire domain to move relative to the background. So effectively, you change your boundary conditions. If you're doing relative motion, you've got to do something to make your mesh move. And there are a couple of different ways of doing it. And this is the method that has become better and better in very recent times, which is mesh morphing. You're basically you're regarding the mesh as a big piece of sponge or foam, and it deflects. You can set it typically so that the regions in the immediate vicinity of the body remain fixed relative to the body. That's a good way of preventing the grid cells from folding over each other. And then you have a smooth deflection back into the background mesh. So you allow it to move up to a certain distance away. And you may use a Laplace solver to get you a smooth distortion of the grid. And these methods have become surprisingly effective. This solution was not intended to happen. This is a boat, a power boat, and I applied the thrust line wrong in the setting up the calculation. And effectively, the thrust line was up here instead of being down here somewhere where you typically, normally with a boat, you put the propeller underwater, not in the air. So in this case, it thought the propeller was up in the air. So it forced the boat to nosedive. And I was rather expecting the whole solution to break when it got to this kind of pitching angle, which is about 10 degrees or so. But the method was sufficiently robust, actually, to not fold up the mesh before it got to this point. A little bit after it got to this point, some grid cell somewhere folded over itself. You get a negative volume and the whole thing blows up. By the way, negative volumes is a feature of meshing for CFD. Typically, when you're dealing with structured meshing, it's quite easy to twist or fold the grid. And you can spend a lot of time chasing down those regions of negative volume because the volume is computed from cross products of the corners. It's quite easy to get a negative volume, even though the concept of a negative volume for us intuitively doesn't make any sense. Mathematically, you can quite easily get a negative volume. And as you can imagine, then the volume shows up in the discretization of the equations, and that completely destroys that. So yeah, the mesh morphing is surprisingly efficient. It's got the advantage that it keeps the topology constant. It also means that you never break any of the grid cells until the point where, of course, you break the whole solution, but that shouldn't happen. And it's really a very good way of accommodating motion, but there's a limit to how much motion you can do that way. So if you need to go to larger motions, and ironically, this is a smaller motion, it's the same boat again, overset methods work extremely well. So an overset method gives you two separate grids where you overset the one on the other. They're also called chimera grids. You can go and look up the meaning of the word chimera and you'll understand why it's used here. So with a chimera grid, you've got a background grid, which is this one here. And then you've got a small grid which is attached to the body of interest and moves as a rigid body with this body. And then your chimera method, or the overset method, overlaps them. You typically want at least 3 cell widths of overlap to get a nice smooth interpolation of the properties between these two grids. And in that way, you can get any complexity of motion because it just changes the amount of overlap, which cells overlap. So it cuts out with each step of the motion. It cuts a hole out of the background mesh and then interpolates between these two meshes. And this is a very robust way of doing large motions. And there's actually quite a well-known aerodynamics code, which is developed by the American Air Force, called overflow. And somebody described to me how they use this method. At the start of a project, some guy would sit down and build up a very high quality structured piece of mesh for each individual component. So he was talking about hanging things underneath helicopters. So you'd have a helicopter airframe, and then you'd have all the different things that they were going to hang under the helicopter. And each of them would be meshed very high resolution and very accurate with a very smooth, high quality mesh. And then they would just combine them as they needed. And the method would resolve the whole question of cutting out holes and two different meshes overlapping with each other. And it gave them a very sophisticated and very accurate method of developing solutions for regions with arbitrary motion and arbitrary complex geometry. So it's an interesting approach, and it's become quite popular again, as it's now been combined with unstructured meshes. It's got the advantage that it allows for very large relative motions. So this is another one of my YouTube hobbies. The modern lifeboat is an interesting thing. You know, they don't lower lifeboats from ships on little cranes anymore. They just throw them off and let them fall into the water, which is quite an interesting, quite a dramatic motion. And in this case, this is a test of a lifeboat being dropped from an oil rig. So it's a very rapid acceleration under gravity, of course, and then it hits the water, submerges completely, and then surfaces and bounces around for a little bit. So you've got people strapped in that boat, of course. So it's quite a traumatic experience for them, but it's a lot better than jumping from an 80-meter high oil platform. So let's take a look at it again, but think a little bit about exactly how much is going on here. You've got a motion simulation. You've got a 6 degree of freedom motion simulation of a rigid body, which is typically the boat. There's an overset mesh attached to the boat, to the lifeboat, which cuts out a hole from the background mesh as it falls. There are some aerodynamic influences which are calculated, but they're very small. And then it hits the surface of the water. So the surface of the water is where basically you hit a 50% volume fraction of air or water, depending on which one you're thinking of. But mixtures of air and water typically solved with a volume of fluid method. So that's an extra transport equation, which basically works out your distribution of the volume fraction of water. So we can just take a look at it. I have seen a video of such a boat being dropped from a crane from a height of, I think, 110 meters. And it's difficult to imagine that would be survivable. And I'm sure it's a pretty traumatic exercise for the people inside the lifeboat, but it's a lot better than trying to do it without the lifeboat. Okay, this is a very nice example of overset, volume of fluid, 6 degrees of freedom motion calculation. So that's it for this little lecture. Are there any questions? Get out of that presentation mode.
Jen's got one.
Okay, let's take a look at that. Shed light on meshed independent study and how it's done accurately. Well, basically, you've got some kind of quantitative answer. Let's say you've got a body, and there's a body in a fluid motion, and it's got a drag. You do a CFD computation with one mesh, say of 500,000 mesh cells, and you get an answer. Then you refine that mesh. You could refine it in every direction, which would give you a mesh that would be eight times larger. So now you've got a 4 million cell mesh, and you do the same calculation again, and you note down that answer. And then you can refine it by exactly 50% in each direction again. So you're going to be another 8 times larger. So now you've got 32 million cells, and you do another solution. What you're hoping to see is an asymptotic trend, that your answer will go to some kind of number that it would be if you had an infinitely large grid. So it's if the thing's very well behaved, you can use Richardson extrapolation. Go and look that up in any CFD textbook. But you can use Richardson extrapolation to work out what it would be for an infinitely fine mesh, or you can find in your particular case it flattens off somewhere between 4 million and 32 million, which is typically what you would expect. And you can find the one that you should be working with. Right, let's get on to the next. Anybody else? So let's take a look now at the other side of discretization, which would be dealing with the actual equations, getting out of partial differential equations. Sorry, I just want to get my chat box back and the share screen.
Yeah, I'm keeping an eye on it. I'll tell you if there's anything.
Okay, thanks. Right, so you see that? So this is now about the discretization of the equation. So now you've got you've got a grid. So the next step is to actually do the discretization of the equations so that you can get to a system of algebraic equations that you can solve. So we've mentioned before, it's two parts, grids and equations. And you need some kind of finite method, be it finite difference, finite element, or finite volume, to get you from a continuous partial differential equation to an algebraic equation, which you can apply to your meshed coordinates. If you were using the same mesh, and it's only really valid if you've got a simple Cartesian mesh, a single mesh where you could use all three methods, finite difference, finite element, and finite volume methods, and you applied the same level of first order or second order differencing, the same interpolation schemes, you should get equations that look exactly the same, or they should at least be equivalent and give you exactly the same answers. Of course, real life is different, so we don't have the luxury of being able to do finite difference on the kind of grids that we're dealing with in CFD techniques today. So let's talk a little bit about the finite difference method. As we've seen, it really is most easily understood on the basis of the uniformly spaced Cartesian mesh, but it doesn't have to be. It doesn't have to be a rectilinear Cartesian mesh. It doesn't have to be uniformly spaced. Delta x does not need to be constant. Delta y does not need to be constant. Just makes it easier to understand if you do it like that initially. But the important thing is the way that you derive your difference equations is you're not looking at a small incremental volume. What you are doing is you're doing a Taylor series expansion of each term in that partial differential equation. So you know how to do a Taylor series expansion, something divided by h squared divided by h third, etc. And then at some point you say you discard the higher order terms. And that basically gives you the order of that approximation. So here's an equation here for second order central differencing, which is a very classic expression. And then there's the equation for second order backward differencing. So it's worth stopping for a moment here. Second order backward differencing is essentially the same thing as, let's call it second order upwind differencing. So the concept of upwind differencing is inherent to understanding what happens with the convection terms in a fluid dynamics method. Remember, we had the four terms, a transient term, a convection term, a diffusion term, and a source term in the transport equation. And the convection term is something that's evaluated at the boundaries of your control volume. So you're looking at the flux of momentum or whatever it properly is, temperature, pressure, not pressure, chemical species, etc., across that face of the control volume, or the finite volume. So it's something that happens on the face, and you're trying to relate what's happening inside your grid cell to what's happening in the grid cell next door. What happens in between them? And that's where your concept of the upwind differencing comes in. So a simple approximation would be to say it's a central differencing scheme, basically taking the average. Let's like a uniformly spaced mesh to start with. It would simply be an average. But of course, it's not like that. A property that's flowing in from upstream is not going to be the average between what you've got here and what you have upstream. It's going to be dominated by what happens upstream. So it makes sense to bias the technique or the scheme towards the upwind side of that particular cell. And that's where upwind differencing schemes come in. So the question is, how far do you take it? You just take it, it's the value from next door, which is essentially first order upwind differencing, or do you extrapolate from the two positions upstream, which would be second order differencing? The difference is important. You need the upwind schemes for convection dominated solutions to be stable. If you try and do this with central differencing, unless your grid's ludicrously fine, the method will be unstable, it will not converge. If you use first order upwind differencing, which is very simple, you end up with a method that's extremely stable and it smears more or less any kind of feature out of the solution. So you get a very diffuse solution. So you need to go to higher order upwind biased schemes to get you both stability, but also a form of accuracy. And this is, of course, where a finite difference method has got a great advantage, because you can just do more terms from your Taylor series. You can just go to a higher order in your Taylor series expansion, because you know where the upstream grid points are and what their values are. With unstructured meshes, where you don't have an IJK structure to the grid, it's not always obvious where the upstream, what the upstream cell is. So upstream or second order or higher order upwind differencing schemes took quite a long time to be developed. However, we've got up to second to third order upwind differencing scheme, even on unstructured grids these days. And that would be your workhorse method. They easily become unstable to destabilize the equations. So in practice, what often happens is you start off a solution using first order schemes, get the solution to a reasonable level of accuracy, and then switch to a second order scheme to refine the solution. So it's really useful to have a CFD program that allows you to make that switch while the program's running, so that you don't even have to stop it. I've seen schemes finite difference CFD solvers with up to fifth order differencing, and that you simply cannot do with an unstructured method. Right, finite difference, that's where you go to learn about the computational methods. You find out what makes what makes something stable or unstable or accurate or inaccurate, and why. You need to understand it at this point, where the grids are easy to understand and the terms are easy to understand, before you can really apply it effectively to unstructured methods. It's got limited practical application. We don't live in a world of bricks like Lego. Lots and lots of curvilinear things that we need to deal with, and lots of very complicated meshes. So the finite difference method is primarily a tool for research and learning. So I am no expert on the finite element method, so I want to talk very little about it, but it is an alternative approach to getting your difference equations. Basically, it should give you equivalence to the finite volume method. As I've mentioned in the previous lecture, although there are finite element CFD codes, there are not many of them, and they're not the dominant ones in the market. We do see them dominating the market for structural software. You could argue that it's based on a much more solid theoretical mathematical basis to deriving the equations, whereas in contrast, the finite volume method is based on actually looking at a volume and balancing out the fluxes through that volume. So the definition given is a procedure that minimizes the error of approximation by fitting trial functions onto the PD. In other words, it's a mathematical approach. You're not following a physical approach. You assume that the solution's got a certain shape, and then you work from there. Okay, I just want to try and take a look. I see there's a question that came up. At what point when using first order can one say it's satisfactorily accurate to switch to second order schemes? Yeah, Andrew's got it right there. When certainly I would agree with that, when the second order solution will run stable. In other words, ideally, you don't really want to start first order. Ideally, you want to start second order. So you start second order. If you find you've got a nasty problem set that is easily divergent, then you start finding ways of stabilizing it. And one way of stabilizing it is to rather run it first order first. And then when everything is nicely settled down, then you switch to second order. If you switch to second order too soon, it'll blow up. If you switch to second order too late, it'll just take longer. There are hybrid schemes where you can blend a certain amount of first order and second order. And sometimes if you get very nasty very nasty kind of equations where you've got something that simply will not settle down in second order for second order accuracy, it's worth blending in a certain percentage, 20%, 30%, first order upwind differencing to stabilize it. Right, so the workhorse of the CFD world is the finite volume method. Once again, it's not necessarily it does not necessarily make it better than the finite element method. It's certainly a more logical fit to the equations, and all the big codes work with it. You're using with an integral form of the equations, so you're inherently enforcing the conservation of all the properties. So this definition is given in some of the literature. Finite element methods create local approximations of a solution using local data and construct a global approximation by stitching them together. In contrast, the finite volume method evaluates exact expressions for the average value of the solution over some volume and uses this data to construct approximation of the solutions within cells. So it's coming at the same problem from two different sides. So there's an interesting natural hierarchy of thinking in terms of cells. So you're integrating that partial differential equation over a finite volume cell, but it looks a lot like the infinitesimal volume that you used in the first place to derive the partial differential equation. So you could do totally algebraic computational fluid dynamics. You could say, well, here is a box of physical size. It's not infinitesimal. Let's apply conservation of mass, volume, mass, momentum, and energy over that physically sized box and do a balance and conservation over the entire domain that way. And that would be exactly the same way of doing it as approaching it from integrating the partial differential equations. The only thing is there's no need to do that because we have calculus. And if we didn't have calculus, we wouldn't have the possibility of working with digital computers to do anything. So one of the very good initial textbooks in computational fluid dynamics was written by Suhas Patankar. And he uses the expression that integrating an already existing partial differential equation over a finite volume cell is a bit like making mashed potatoes from dehydrated potato powder. Normally you would take the potatoes, you cook them and just mash them. But what we're actually doing is we're buying a dry potato powder, dehydrated potato powder, which is your differential equation. And you're adding water to that to reconstitute it. But it was previously cooked and mashed and then dehydrated. So that's an interesting way of thinking of the equations. Okay, questions at this stage? Anybody? Okay, so let's get into the final part of this lecture, the final bit of the graveyard shift on a Friday afternoon. Actually solving the equations. So we've basically got all our building blocks. We've got our mesh. We've got the equations discretized on that mesh. Okay, well, thank you for that, Sonal. And now you've got to turn it into a solution. Okay, so this is, once again, we can think in terms of this question of this hierarchy. You've got the original partial differential equation derived on an infinitely small cell. Then you've got a finite cell, which you've done your numerical integration over to get your algebraic equations. But if you were doing CFD in parallel, yeah, that's a more difficult question. I'll answer that in a moment. If you're doing a CFD in parallel, you're taking your entire domain, which is, say, 10 million cells, and you're breaking it up into smaller collections of cells. So once again, so that whole concept of working with a range of cells remains a logical one. And interestingly enough, the earliest forms of parallelization of CFD codes was to take that multi-block grid that we showed you earlier. We've got 1,000 blocks making up a grid of, say, 4 million cells. And you assign the individual mesh blocks to individual processes in a computing cluster. So you can work on, they've got to be solved sequentially anyway. So you might as well solve them in parallel over many different computers. And at every iteration step, at the end of each iteration steps, the blocks, individual blocks, communicate with each other and exchange boundary conditions. Now, the same thing applies when you're doing a parallel solution of a single large unstructured mesh. Is you decompose it first. You decompose it into the number of computers or computer processes that you're going to be solving it on. And each process takes a collection of these cells, does the solution on that, and at the end of the iteration, exchanges boundary conditions with the other partitions. A multi-grid solver, which is something you use to actually solve the linear system of linear equations, solves them by working through a hierarchy of agglomerated cells. In other words, you group a bunch of cells together, put the values together, solve that, and then you break it up into smaller bits and pieces to do each of them individually and bring them back together again. So you're going up and down this hierarchy of cells. Okay, Khaled asks, can you explain the defects of finite elements and why I need another method? As I said, I'm no specialist on finite elements. And once again, trying to do that in the scope of this lecture or so is far too much. The explanation that I've been given is that in fluid dynamics, most importantly, you're trying to maintain conservation of all your properties: momentum, conservation of mass, conservation of momentum, conservation of energy, conservation of volume fraction, conservation of chemical species. So when you are completely focused on keeping the method conservative, then working with integrating all those volumes over each individual cell and maintaining conservation in each cell is a very effective way of maintaining overall conservation in the whole system of equations. So what your finite element method is doing is it's assuming a shape of variation through your cell, and that does not necessarily give you conservation of the properties. So how can I decide the convenient method to the problem? Well, you don't sit down one day and decide, I want to solve fluid dynamics numerically. I'm going to now choose a finite different method or a finite volume method, because you'd be starting off where everybody else was 40 years ago. So you don't do that. You start off from existing frameworks for developing codes. So for fluid dynamics, if you're going to be working in fluid dynamics, you want to write your own stuff. One place where you can start is OpenFOAM. OpenFOAM is a collection of libraries that you can use to write new solvers. It's wasn't originally developed for using as an out-of-the-box tool. It was developed as a way of making it easy for you to develop your own solvers. So you've got building blocks that you don't even need to think about the parallel processing. That's already been built in. You don't need to think about the input and output. That's already built in. You only need to think about your equations and what schemes and things you want to apply to your equations. So that frameworks exist. If for some reason you had a good reason to work with a finite element library, you could do exactly the same thing with a finite element library. There is, for example, a code called deal2, which is exactly that. It's a set of building blocks for developing finite element solvers, and people have developed fluid dynamics solvers with the deal2 tool set. So you would start there. You wouldn't start from scratch and write your own thing. You'd decide which of those libraries would be better for answering your particular question. Right, so let's move on here.
Oh, can I make a quick comment, Charles? Sorry to.
Please do.
The one place where I suppose there might be a slightly more finite element fluid solvers possibly have slightly more traction is for multiphysics codes, where you're trying to solve structures which are interacting with a fluid mechanics problem, and maybe something, yeah.
Definitely true.
Yeah.
If you don't want to couple different methods externally, but you want to do it all internally, there would be some merit certainly in doing it with finite element, I'm sure. So, okay. First time I went to an applied mathematician, and I said to him, I need your advice on which solver to use to solve the set of linear equations I get when I discretize the Navier-Stokes equations. He answered that with a question instead, and he said, if you've got a set of non-linear Navier-Stokes equations, why are you wanting to solve it with a linear solver? Which is a very valid question. I didn't have experience at that stage to answer it. But of course, it turns out that if you want to solve, your methods for actually getting the equations solved involve a lot of iterations. So you're actually better off with linear solvers dealing with the algebraic equations than trying to use non-linear solvers for the basic equations. But that illustrates a dividing point between the different fields. So structures, we've talked about linear structures, in other words, things where Hooke's law still apply before you get plastic deformation. We're not talking about fracture and contact and so on. They're all nice and linear, so your basic structures are easier. You don't really have linear flow equations, but fluid dynamics developed a long way by making certain assumptions to make it more linear. So first of all, there was the development of potential flow, which was from the early days of fluid dynamics, where you're assuming the flow is continuous and irrotational. And you bring in the irrotational, which is really a non-physical concept, whereas continuity is a very physical concept. You end up with a fluid dynamics equation which is linear. And then you can make it very easy for yourself by combining simple solutions to simple flows to build up to something complex. And there's a whole library of methods that we use, especially in aerodynamics, along that basis. But you can also do other simplifications to the Navier-Stokes equations, basically to make them better behaved. So there's the Euler equations. If you drop the viscous terms, the diffusion terms, which is quite a good assumption for high Reynolds number flows like aircraft and so on, for example, you get Euler equations, which are somewhat stabler and easier to solve, and you've got fewer equations and things to solve. You don't worry about turbulence models. Then there's the boundary layer equations, where you can remove a lot of the gradient terms because they're dominated by the shear in the boundary layer. And then for higher Mach number flows, you've got thin layer and parabolized Navier-Stokes equations, which effectively did away with effects that propagate upstream. So you can march your solutions downstream, and they become much easier and much faster. But unfortunately, most flows are not like that, so you need other methods. And we've touched on this before. You've derived your Navier-Stokes equations. So you've got an equation that looks like this for each velocity component. So this is an incompressible flow, but that doesn't really matter in this context. And then you've got a continuity equation. So you've got three momentum equations. You've got one continuity equation. So this is the x direction momentum equation. The y direction momentum equation would have had a v in there. Doesn't matter. It's basically, they all look the same. The point about them is you've got an equation for each velocity component, and you've got a continuity equation which does not contain the pressure, but you now still need to resolve the pressure in some way. So where do you get that pressure from? And it turns out to be not such a simple answer. So originally, and once again, this is an illustration of how clever people are when they don't have good computers, is the development of the stream function and vorticity approximation or formulation of the equations. It's limited to 2D flows, which is its real shortcoming. It's got some funny issues around boundary conditions, etc., but those are easily resolved. But the biggest problem is it's only really defined for two-dimensional flows. But it was widely used in the early days of CFD because you effectively coupled it by combining two of the equations through the introduction of two additional concepts, which are the stream function and the vorticity. So basically, vorticity is related to viscous shear, and stream function is related basically to your conservation of mass. If you cross a stream, the value of the stream function increases. If you go along a streamline, the value of stream function remains constant. A streamline is a line of constant stream function. So if you express the equations in terms of the stream function and the vorticity instead of pressure and two velocity components, you end up with just two equations, one of which is very simple and another one which is a classic form of a transport equation. You don't find any explicit pressure in there. And because you've now gone from 3 equations to 2 equations and you've solved the coupling problem, these methods were incredibly fast, but limited to 2 dimensions. If you tried to extend them to 3 dimensions, you ended up with more equations than with the Navier-Stokes method. So that limited its effectiveness. However, the problem with incompressible flows was solved with the development of the so-called simple algorithm. And the simple algorithm is the semi-implicit method for pressure-linked equations. Because it's such a nice acronym, it spawned a whole industry that tried to develop different methods. It was some variant of simple. So simple was followed by simpler, which was the simple revised method. And then there was a simple extended method, which was simplexed. And then somebody else came up with a simplest method. And then there was a simple C method. All of which did more or less the same thing, but different in some detail. What we've seen is you try and solve the momentum and continuity equations sequentially. You don't actually get to the solution because you don't have a way of extracting the pressure from that system, because it's not a coupled system. You're going through the equations sequentially. So the solution to that was to assume that you had to deal with an iterative method. And then within that iterative method, starting from the discretized continuity equation. So you take your continuity equation in its differential form and developed a discretized version of it. And then you worked further with this discretized version and you started substituting in that everything was this value plus an increment. In other words, a starting value plus a change, so that you could try and find an expression for that change in pressure from one iteration to another. Because what you're after is a pressure correction equation, a delta P. Given a pressure at this iteration, if you move to the next iteration, how much does the pressure need to change to drive the equations in the direction of now satisfying the continuity equation? When you write the equations out that way, this discretized equation, you end up with an insolvable long equation with a lot of things you don't know the value of. But it contains several terms that would go to a value of exactly 0 when you reach convergence. And that allows you to just drop those terms, because when you've got convergence, your pressure correction must be 0 anyway. So dropping the right terms from this equation allowed you to develop a much simplified pressure correction equation. And the variants on the simple method were all based on the idea of trying to make that bit that you're dropping as small as possible, hence simple consistent or simple revised, to try and make that dropped term smaller, because that would get you a faster convergence. But it assumes that you're going to always be iterating, so you never solve for the absolute pressure, you always solve for the pressure correction. So this is what it looks like when you express it in flowchart term. You guess a pressure field, then you solve the velocity using that pressure. Then you work out what the corrected pressure is. And with that corrected pressure, you can correct your velocities and your other properties, and then you go around it for another loop. And this method was developed in the 1970s already, and it's still in use, and it's still used in a lot of methods. It's very well developed. It has got a good ability to be tuned for stability. Anything more to say here? Where it breaks down is where you've got compressible flows. Compressible flows have got other methods that work for them. If you try to apply the simple method to compressible flows, yes, they work, but they become incredibly slow. One of the advantages of the segregated methods, or the simple family of methods, because you're solving equations sequentially, you're only at any given time solving one equation. So it keeps your peak memory requirement for storing the matrices involved in solving that equation. It keeps down to a reasonable level. At one stage, this is a very big advantage, but of course, since then, two things have happened. Memory has become very cheap, So you can have a lot more memory per processor, and then parallel processing has become the thing. So you don't solve a single large flow domain on a single processor anymore. You distribute it over a range of computers, so you've got access to more memory that way anyway. So memory requirement for CFD, although it was a very, very important thing at one stage, is almost unimportant these days. You just want fast memory. So the disadvantage of the simple method is that your convergence can be relatively slow, especially if you've got a lot of complicated physics that get added in, and especially if you start adding compressibility. But then there are better methods to use. But you can normally find some way of forcing the solution to be stable. It illustrates the point that you've got 3 levels of iteration in a typical solver. Your partial differential equations are already fundamentally nonlinear. They've got nonlinear terms. So you're always going to be iterating to solve them. The simple method only works as an iterative solver. And then you've got large linear systems. In large linear systems, you can't solve with direct solvers. You always solve them with iterative methods anyway. So you've got multiple levels of nested iterations. Compressible solvers used for higher speed flows developed along a completely divergent path because they don't suffer from the difficulty of the pressure velocity coupling, because you can couple them by way of an energy equation. You have to solve the energy equation anyway. And the energy equation's got the temperature and the pressure, and the temperature and pressure couple to each other due to with a combination with the addition of an algebraic equation of state. So you don't need a special mechanism to resolve the pressure velocity coupling, provided that the flow is sufficiently compressible. If you're trying to apply these solvers to very low speed flows, they fail unless you've got some kind of pseudo compressibility that you bring in there to make them numerically stable and convergent. So this is what this typically looks like, is it becomes a single coupled set of equations. So you solve these equations together. Your conservation of mass equation, your conservation of momentum equation. So I'm showing 2 here, but you're going to have 3 of them. You would normally have 3 of them in 3 dimensions. And then you've got an energy equation. So it's a transport equation. It's coupled, but you need to pay special attention to how you split up these flux vectors to get stable solutions, because they've got different properties. You've got scalars and you've got vectors, and you've got diffusion terms, you've got convection terms. So this has to be split up carefully in order to get a convergent solution. So a fairly recent development has been the development of pressure-based coupled solvers. In other words, combining the features of the previous 2 methods. So one of the disadvantages, of course, of the density coupled solver is 2 disadvantages. One is it needs a lot more memory, because you're solving 5 equations at the same time, 5 or 6 equations at the same time. But memory, as we've seen, is less of an issue. And then the density-based solvers basically fail when the density changes become very small, as you get into incompressible flows. So applying some of the thinking of both methods together have now given us pressure-based coupled solvers. And these today would be in most methods where they're available, you would probably be your starting point. It's a quite close run thing, whether you'd be using a pressure-based coupled solver or a segregated solver, like a simple family of solver, when you're dealing with an incompressible flow. There's no clear winner there, because it rather depends on the particular conditions of each solution. So very often you may find that you have to try either or both of them to find the one that suits your particular problem best. It's got a lot to do with some of the detailed numerics that happens in the corners of the grid. The approach is basically similar to the density-based solver, but instead you're still solving a pressure correction equation. You've still got no way of solving the absolute pressure because of the incompressibility, but you're still solving a pressure correction equation, but you're now formulating the pressure correction equation on an implicit term. In other words, the values from the current value of the solution. This took a long time to develop, so it's only recently become available. And you still need some preconditioning of the matrix to get it into a form that it is can sensibly be solved. You would generally expect better convergence. It certainly needs a lot less iterations. So it's a feature of the segregated solvers that you need thousands of iterations. It's really not atypical to, as a starting point, to think in terms of, for a steady state solution, needing somewhere around 1,000 or 2,000 iterations, and I've seen as high as 30,000 iterations to get a single converged solution on a steady state. Whereas your pressure-based coupled solvers may converge in 100 iterations. But the individual iterations do take a lot longer, so the actual difference in total solution time is not necessarily that spectacular. Okay, so it's classifying those methods and then the actual solution of the linear equations. If you go back to your finite difference approach to starting fluid dynamics, if you do a single one-dimensional case, it's quite easy to build up a tri-diagonal matrix algorithm to solve the equations. In other words, the value at each grid point is only related to its immediate neighbors. So if you're solving a system of equations, there's only ever 3 elements on the diagonal of the matrix. So solving that's very easy. You can just go run down it and run back up it to solve it. It solves very quickly. So it illustrates the point of sparse matrices. CFD matrices are inherently sparse. If you're dealing with a single dimension, you've only got 3 elements on the diagonal of the matrix. If you're dealing with unstructured methods and more dimensions, you start adding more elements and they're not necessarily on the diagonal. So it's one of the key elements of solving these equations is to restructure that matrix to get the elements closer to the diagonal, because you don't want them scattered all over the matrix, because that's quite bad from a numerical point of view. Also, from a memory point of view, you never store the entire matrix, you only store the non-zero elements. So although the structured grids can be solved with structured solvers, linear, so variants of that tri-diagonal matrix algorithm approach, or Thomas algorithm, in general, nearly all codes now use unstructured solvers, even for grids that are originally developed as structured grids, because the unstructured solvers have become so efficient. So you never use direct solvers because the matrix is just far too large. So the typical kind of solvers used is, if you're still working with structured methods, they still use successive line over relaxation. In other words, instead of using a line-based method to solve a one-dimensional problem, you're using that same line-based method, but you're scanning it in various directions through the blocks of the grid. But the unstructured solvers take a different approach, using either conjugate gradient solvers or bi-stabilized conjugate gradient stabilized bidirectional conjugate gradient methods. But the current trend is to rather use algebraic multigrid methods where you can, because that's an efficient way of dealing with these very large matrices. You don't have to deal explicitly with a multigrid. There have been several CFD codes which solve the equations using multigridding levels, hierarchies of grids explicitly. In other words, you had to generate a series of grids, and your solution was solved on a sequence of grids of more and more refinement. And you had to be quite careful about assigning your number of grid points on your fine grid so that it could be divided by 2 a number of times to coarsen the grid. Now, mercifully these days, the algebraic multigrid solvers take care of that at matrix level. So you don't have to worry actually about the grids themselves, about coarsening the actual grids. Okay, so there's a question here. What do you mean with matrix extremely sparse? Okay, so you've got a partial, so you've got a partial differential equation which is approximated with algebraic equations through a grid, and basically relates the properties at a position in the grid with its immediate neighbors only. So if you think for a moment about a hexahedral mesh, one that's built out of bricks. So you've got a single brick, one on top, one below, one that side, one that side, one that side, and one that side. So it's got 6 neighbors. So this particular grid cell gets its value related or expressed in terms of the values of its neighbors. Higher order schemes may take it out one extra layer of grid. But typically, let's stick with first order methods because it's easier to understand. You could say that at each grid cell is only related to its values at its 6 neighbors. But a certain mesh may have 60 million cells. That's not an unusual size of mesh for a CFD solution. So you've got 60 million of these grid cells, but each individual grid cell is talking only to its neighbors. It's only influenced by its neighbors. So your total matrix for this equation, we're only talking about a single equation here, is a 60 million by 60 million matrix. So it's a huge matrix, 60 million by 60 million. But on any line in that matrix, there are only 7 elements, only 7 numbers that are not 0, which is the node that you're talking about and its 6 neighbors. So if you're expressing that as a system of linear equations, how do you solve a system of linear equations that's nearly entirely zeros? It's almost entirely zeros, except for those 7 elements in each line or column that are not 0, which is related to your neighbors. So yeah, I mean, you would never ever save a 60 million by 60 million matrix. It just wouldn't make any sense. So you only save the values and their position in that matrix. And there's a whole family of methods that have been developed for solving sparse equations. And that would typically be your conjugate gradient methods and your algebraic multigrid methods. Okay, so this last bit, I think it's a little bit rushed because doing anything else with it is a lot more work because there's a lot of theory that has to be followed consecutively to get you through this process. And that's why I say this is the sort of thing that you should be doing in a university course. What I'm trying to get across is if you're going to be working in CFD and you need to get to the bottom of these methods, these are the things that you now need to go and study to make sure that you understand them. Okay, so do you mean related to computational expensive? Okay, I don't actually understand what you're asking there. Yeah, okay, so you couldn't save a 60 million by 60 million matrix because so much memory just doesn't exist in a single computer. But you don't need to, you only save the ones that you need. So computationally expensive is 2 things. It's the amount of memory that you need to save. Yeah, okay, that's a lot. So yeah, so computational expense. Computationally expensive is 2 things. It is the amount of memory that you would need to store it in memory, but also the number of floating point operations that you need to process it. Because floating point operations take time, and time is money, but they also take energy because the CPU consumes energy as it runs, and it's a significant cost of energy to solve these equations. To give you an idea, our Lengau cluster, which has got 33,000 cores in it, consumes about 800 kilowatts of electricity to run. So 800 kilowatts of electricity. Those are some very thick cables. It costs money to run a system like that. Another interesting thing about the peculiarity of fluid dynamics equations, and this applies to any kind of sparse matrix equation. Paradoxically, because the matrices are so sparse, you actually need relatively few operations on each. You need relatively few floating point operations at each iteration to get your solution. But you do need to move an awful lot of numbers from the memory onto the processor. So the performance of the code, the speed at which the speed can execute, is not limited so much by the speed of the processor, but by the speed of the memory. We find, for example, that you can compare 2 computers of quite different architecture, an Intel and AMD and an IBM processors, which got very, very different microprocessor architecture. If they're being fed by the same kind of memory system, you find that the performances for things like CFD codes would be near identical. Okay, that's it for this particular lecture. We'll stop the share there. Okay, any questions at this point? It's actually, so that's not even, so that's even a low estimate of the amount of memory that you need.
A double is actually something like, what is it, 32 bits or something like that. So
yeah. So no, that's why any sparse matrix system, you know, the way that you save the matrix is critical. You cannot save a full matrix. It's not even, you can't even contemplate it. You wouldn't even do it for a small development code. Okay, any other questions? Okay, so when we resume on Tuesday with these lectures, I'm done with theory lectures for now. On Tuesday, I'll just give you a bit of a demonstration of how this is applied in some commercial programs, for example, mesh generators and commercial CFD solvers. And then on the last session on Thursday, I'll just walk you through OpenFOAM, some of the mesh generation tools in OpenFOAM, post-processing tools in OpenFOAM, and then also how to use just the structure of the cases in OpenFOAM, how they set up and how you change parameters for those cases. Francisco, welcome back.
Yeah, Charles, sorry. Sorry, this morning, this afternoon when your talk started, my electricity disappeared. That's why I struggled for a while to join the meeting again. And yesterday, we started a tradition that we offer a book voucher to the participant that asks the most interesting question. Yeah. And I should have warned you earlier, but then with the electricity going, somehow I lost my plot. I don't know if you have, you can already decide upon who had the most interesting question, or we give people still a chance to ask the most interesting question.
I think we need somebody to. Well, I think one more question. If somebody wants to throw another question.
Okay, one more question. So there is. Yeah. Okay. Here comes an interesting question.
Let's take a look.
It's in the chat.
Okay, well, it might be interesting to you. I make no claims to being able to answer that.
There's a method used in turbo machinery sometimes where they basically use a truncated Fourier series to model the blade weights, because that's the only thing I can think of which is vaguely analogous.
Yeah, so that's, I'm not going to comment on that. So if Andrew wants to comment some more on it, he's welcome, but I've got no more comments to add to that.
Well, I'm only inferring that it's something similar to what he's asking.
Okay.
So,
I don't know, does Scarlett want to maybe to make his question more explicit to get the opportunity to win? We can ask, okay.
Cheers, Solomon.
We can give him, yeah. Okay, there is no more reaction. So we will we will think about who won the competition this afternoon. Yeah.
Okay.
Yeah. Okay. Then please don't forget that this afternoon at 5 we want to have a social virtual event, and you find the link in Moodle. Yeah. So please join us there. Yeah. And I see that Khaled added a remark to his question. Yeah. You know, I know from my time many years ago, those Fourier and Galerkin methods were used quite a lot in the study of turbulence. for various reasons. Yeah. So
Okay.
yeah. Good. So maybe we award the prize today to Khaled because he's really trying very hard. Yeah. So Khaled, please email me your email address so we can make a plan for the book voucher. Okay.
So
then
that's it for today.
thank you very much. Here comes the email. Perfect. I will write it down. Thank you very much. Then we will see you hopefully at 5 later this afternoon, or latest then on Monday morning, fresh for the next series of lectures. Yeah. So thank you very much, everyone. Thank you, Ilya, for setting up the link. Thank you, Charles, for the nice presentation. Andrew, for the comments. And sorry that my internet connection was disappeared at some stage. Yeah, but that was beyond my sphere of influence. Yeah. Thank you.
Okay. Goodbye, everyone.
Bye. Bye-bye.
Thank
Have a
you.
good weekend.
Bye.
Goodbye.
Bye.